Assalamualaikum warahmatullahi wabarakatuh. So we meet again. So this is the lesson for single phase full wave rectifier SKE 4433 power electronics. So in the first part of this topic, we have already discussed on the what we call the half wave rectifier. So we have already discussed on the control and uncontrolled, where uncontrolled is actually we have discussed on the using the diode with different load, which is R and RN load. And for the control also we have discussed about um, the using the SCR as the control half wave rectifier with R and RN load. So for this topic, this subtopic, we will go discuss on the full wave rectifier. So full wave rectifier, we have actually two circuit type or topology type, which is we call bridge, okay, and the second one we call the center tap. So this center tap meaning that we are using transformer as the electrical isolation, which is to provide protection of the source from the load side. While for the bridge, we didn't have any protection. We didn't use transformer. So it's actually a connection of the load and source is actually a direct connection. Okay, and both circuit will also be discussed based on control and uncontrolled uh, power devices. So we are using, okay, we are going for the uncontrolled full wave, which is the first circuit, which is a full bridge. So the figure below shows the circuit diagram using the 4 diodes. Okay, so as you can see, this is what we call the full bridge. Okay, and sometimes we call this one as a H bridge. So in powertronics, so if we have one leg, we have two legs. So if we have two legs, so this is considered a full bridge. So if you have only one leg, we consider as a half bridge. Okay. So this circuit we will analyze based on the first one. We are using a very simple circuit, a very simple load, which is the R load. And in a general form, okay, in a general operation, so for positive cycle, so this is uncontrolled, meaning that the forward bias and reverse bias of the diode is determined by the polarity of the source. So for the positive cycle, based on this connection, okay, D1 and D2 will actually conducted, while D3 and D4 will be automatically reverse bias. So D1, so the current will flow from D1 to the load and go back to the source through D2. While when the negative cycle here, so the polarity is reverse, so D3 will turn on, okay, with D4 going back to the source, while D1 and D2 will actually turn off. So as you can see, for each leg, only one diode will actually operate it. So if D1 is on, D4 will automatically off, while for if the D3 on, D2 will automatically off. And the reverse bias voltage, meaning that the blocking voltage for non-conducted diodes is equal to the peak value of the source. Okay, for example, for the positive cycle, D1 is on while D4 is off. Okay, so based on the KVL here, we will see that the V block or the V blocking or the V reverse bias voltage for the D4 is equal to the peak of the V source. Okay, so in other words, this also reflect the V rating of the diode. So if you want to buy the diode, so this is the analysis that you need to do before you purchase or you buy the diode. Okay, so this is the waveform of the uncontrolled full wave using R load. Okay, as mentioned before, so this is the output voltage. As you can see, every half cycle, positive, negative cycle, the output has the output. Okay, unlike the halfway where you only have the output during the positive cycle. But for the full wave, we have both positive and negative. We have both. Okay, we have our output, and this is the voltage waveform across diode D1 and D2. So as you can see, when the positive cycle D1 and D2 is on, so that's why we have zero voltage drop here, no voltage. But when negative cycle D1 and D2 off, okay, and it will actually have some blocking voltage appear across the power switch, the diode, which is equal to the VM, okay, negative VM, which is the Vmax of the source, and this is repeated for the next cycle. Okay, and this one also is the voltage across diode number 3 and diode 4, and as you can see during the positive cycle, D1 is on while D3 and D4 is off. So as you can see here, they will appear a voltage blocking value here, waveform, and the maximum value is equal to the source, negative VM. And during the negative cycle, D3 and D4 is on, so that's why we have no voltage drop. So the voltage is zero here, but we can see D1 and D2, there's a voltage blocking. And this is the output. Since we are using R load, so the output waveform is following the voltage waveform shape. Okay, and this is the current of diode D1 and D2. So of course, when diode D1 and D2 are on, so there will be a current flowing, while when they are off, the current is zero. So vice versa with D3 and D4. So during the positive cycle, D3 and D4 are off, while during the negative cycle, D3 and D4 are on. So the I out is actually the summation of all the current that going through both all diodes. So I out is actually the summation of these two waveforms. And the I source, as you can see here, is a pure sinusoidal, which is in phase with the uh, voltage input. And this is the equation of the average output DC voltage. Okay, so this is for the full wave rectifier. As you can see, we have 2 times bigger. Okay, for the half wave, if you may recall, the V out average is Vm over pi, but for the full wave, we have 2 times more output voltage average. And since it is R load, so the I out average can be simply calculated by using V out average over R. And the power absorbed, as mentioned earlier, you need to use RMS value. Okay, where RMS, since for the IRMS is actually IM over square root 2. And the power factor are 1. And this is the second type of circuit for the full wave rectifier. Okay, so we call the center tap. So as you can see here, we are using transformer, center tap transformer. The function of this transformer is for electrical isolation, for protection. Okay, and we are using 2 diodes. Okay, the advantage of this center tap circuit is that it provides electrical isolation for protection, and the second one is that they have less numbers of diode use. For the full bridge, we use 4 diodes, but for the center tap, we only use 2 diodes. So in terms of structure wise, so center tap has obvious advantages compared to the full bridge. But there are also some limitation for this center tap circuit, where we will see that after this, that the voltage rating, the voltage blocking that need to be actually applied, okay, not applied. So actually need the voltage blocking capability of the diode used for this center tap is actually twice of the peak of the source. For the full bridge, the rating only at least equal to the voltage source maximum input, but for the diode used in this center tap, the voltage capability must be at least twice of the peak of the source. So that is one of the limitations of this center tap. But both circuit, full bridge, and center tap, uh, they have their own advantage and limitations. Okay, and it actually depends. There's no circuit that is good. Okay, it depends on the applications. If you are more concerned on the protection, on the isolation, so this center tap provides better solutions. Okay, but if you are have limitation in terms of budget, and I think it's better to have the full bridge, because diodes with lower uh, rating voltage is much cheaper compared to the diode that has higher voltage rating. So the output, as you can see, the output and the output voltage and the output current are the same, okay, with the full bridge, because they are full wave rectifier. But as you can see here, the difference is on the voltage blocking of the diode D1 and D2. We have, as you can see here, for diode D1, the voltage rating must at least equal to the twice of the V input. Same with the VD2. And this is the current output, same. So this is I1, diode I1, and this is current diode 2. And the summation of these two diodes is actually similar to the I output. And this is I source, which is similar with the waveform of the voltage source. So meaning that the power factor is equal to 1. And this is actually good, because our main concern is actually to get the input to be always in unity power factor. And the same equation are applied for the center tap. Okay, and example 1. So the source peak voltage, so very simple. This give you 120 volts, so meaning that you need to PM is equal to square root 2 multiply 120 volts. So you should have 100 and around 169.7 volts, and the average voltage is actually 2 Vm over pi. So this one is equal to, just using calculator, very simple, 108. And the average current is, since this is R load, very simple. So 108 over your R load is 18. Okay. So you should get 6 ampere. And if there is a question, what is the power factor? So the answer is unity. And this is the example 2. So a single phase rectifier has a resistive load of 25, determine the average current and peak reverse voltage of each diode. So a bridge rectifier, meaning that the peak reverse voltage or the blocking voltage is must equal to negative 200 multiplied with square root 2, which is the Vmax. Okay, so this one is 100 and must be negative 169 0.7 volt, while for the center tap, okay, the peak reverse voltage rating must be multiply of negative 169.7, which is around 339. So you need to have a diode that has this rating, okay, for the center tap. For the full bridge, you only need the diode to have at least equal to the voltage source. Okay, so this is the full bridge. We continue with the full bridge RL load uncontrolled. Okay, so as you can see here, we have L inductor, which has inductor here as a storage element here. So so definitely the current will be no longer linear or sinusoidal. So the current, as you can see here, the output is actually has some nonlinearity compared to the voltage. So the voltage is actually perfect sinusoidal. It's a perfect what you call rectified sinusoidal. So meaning that the V out average is actually similar. We can use this equation 2 Vm over pi. But the current here is nonlinear, which is you need to derive. Okay. So as you can see here, during the first cycle, okay, during the first cycle of this, okay, so D1 and D2, okay, D1 and D2 will turn on. Okay, so the current will actually increasing because the inductor is charging, okay, increasing. Okay, and then at some point here, where at the pi, where the polarity of the voltage source is reverse, going to the negative cycle, okay, so the inductor will start to discharge, okay, okay, but D1 and D2 will turn off, okay, because of the reverse direction of the reverse bias, and D3 and D4 will turn on. Okay, so this inductor need to be discharged. Okay, unlike the half wave where there is no route or there is no path for the energy of the inductor to be discharged, so that's why they force the single diode to turn on. Okay, but for this half wave, okay, the energy will discharge through D3 and D4, okay, because D3 and D4 are turned on during the negative cycle. So the energy will be discharged through the load and also the voltage through D3 and D4. Okay, and this cycle will actually repeat it again and again. So this is the voltage source, and as you can see, the current source is no longer sinusoidal, which is actually take the shape of the output current. Okay, but as you can see, for the positive, so the current is positive, but the negative, the current is actually revert to the negative value here. So meaning that this current is actually actually distorted current, which means that it has some what I call harmonics. Okay, and the power factor is no longer equal to unity. Even though you can see that this power factor is actually in phase with the voltage, but please be noted that the power factor is measured based on the sinusoidal voltage and the sinusoidal current. But this one is no longer sinusoidal current. Okay, We want to see this, actually this slide is actually we want to see the effect of when we have what happened when we have the inductor is very large compared to the resistor. Okay, so when the inductor is very large, okay, this conclusion that we can say that the current instead of this non-linear current output, when the inductor is very large compared to the resistor, the current will behave as a DC current. Okay, will behave as a DC current. And this is the diode, is the current going through D1 and D2. Okay, during the positive cycle, the negative cycle is off, so there is no current. While this waveform shows D3 and D4 current waveform. During the positive cycle, there is no current flowing because D3 and D4 are off. But for the negative cycle, as you can see, D3 and D4 are turned on, and that's why we have the current flow, which is also a DC. So the summation of these two current that flowing from D1, D2, D3, and D4 will actually produce the I output. And this is V output, still rectified sinusoidal perfect. And this is the current output, which is just a square wave, positive, negative, positive, negative. Okay, and due to the current output is a purely DC, meaning that the IRMS is also equal to the current I out average. So how it is happen? Why when omega L is larger compared to the resistor? So this is how we prove it. Okay, so let's consider that using Fourier series, the V out, which is the rectified sinusoidal here, can be written in terms of Fourier coefficient, which is we have the V out as your DC term, and we have what you call AC component, which is Vn cos n omega t plus pi, where n is actually a number, even number, and this Vn can be computed by using this one. So this Vn we call as a harmonics component. Okay. And the current can be computed by using this equation. So I out, which is the DC component of the output, can be directly computed by using V out over R, while for the AC component of the Fourier, which is In, we can compute by Vn over Zn, where Zn is actually R plus Jn omega L, and this n is actually even number 2, 4, 6, and so on. So as n is increased, okay, so when n is increased, we can say that Vn will decrease and Zn will increase. So based on this relationship, okay, Vn decrease, Zn is increased. So meaning that I can say like this. So Vn is increased, reduce, and Zn is increased. The In will actually decrease, okay, rapidly for increasing of n. So meaning that this In, okay, so when this is almost will actually increase. So if you use omega L, which is very high compared to this resistor, Zn will actually increase much more bigger than the decrease of the Vn. So meaning that the IRMS, which is can be computed by using this equation, I out DC component plus the summation of all the AC component. So since In is reduced, meaning that this can be considered as a zero, so meaningless, okay, because the value of In is almost very small compared to IO. So in final word, okay, we can actually shows that why when omega L, if omega L is choose to be very large to the resistor, the current will almost become DC current, because we consider this one is negligible. Okay, meaning that the current value or the current magnitude for the AC component is very, very small, because as you can see here, if omega L is choose to be very large compared to the resistor, Zn will become more, it become higher than the Vn. So please be noted that this is a very favorite question to be asked during your test and also your final exam. Okay, issue to the related to the supply current. So actually, when you are using rectifier, definitely you want the output to be a pure DC voltage and DC current. Okay. Okay, so usually we can achieve that by using inductor or capacitor as the load. But our concern, which is not covered in this syllabus, is actually at the input side. Okay, so as you can see, when we have the inductor of the load is higher than resistor, yes, you have a DC current, which is, that is the objective of the rectifier, to have DC current. But you may notice that the current source that TNB, our voltage supply, is facing is actually a square wave, not sinusoidal. So this will actually be a problem to the our TNB supply, because the TNB in a power system, they want the voltage and current to be always sinusoidal and are in phase. But due to the rectifier, due to this rectification process, the current source becomes square wave. Okay, so this is the main issue that faced by the TNB. Okay, and usually to solve that, what TNB done is actually actually place a filter at the input side of the rectifier. Okay, meaning that this is your rectifier from AC to DC. Okay, which this one produce DC current, but the output side will produce a square wave. So before going to the TNB, it will set a filter, so RLC filter. Okay, RL filter, meaning that after filtering, the TNB will see that the current is sinusoidal. Okay, so this is actually what I call the filter that added at the input side of the rectifier. So we only continue with the example 3. Okay, so example 3. So actually number 1, determine the average current in the load, is actually referring to the DC component of the current output current. So the DC component of the output current can be simply calculated by using V out average over R. Okay, where your V out average for the full wave, since your output voltage is actually rectified sinusoidal, so it's actually just 2 pm over pi. So which is 200. Okay, 200 over pi. So this one should be 200 over pi multiplied with the R load, which is 100 ohm. So you should have 2 over pi, which is 0.63. Okay, 0.36 ampere. So this is your average or the DC component inside the current load. Okay, and then the second one, determine the first 2 higher order harmonics of the load. We could we should notice that, or I recall, the IN is actually referring to the harmonics of the current. Okay, so you can compute this by using Pn over Cn, and the first, where n, the harmonic is actually 2, 4, 6. 8n is actually an even number. So for the question, determine the first two higher order harmonics. So meaning that you need to have n equal to 2 and also n is equal to 4. So meaning that you need to find what is your I2 and harmonics current I4. Okay, so I2 is actually V2 over Z2. So what is your V2? So what is Vn? Is actually referring to the our slide. Okay, where our slide shows that the Vn is actually 2 Vm over pi 2 Vm over pi multiply with 1 n minus 1 plus 1 n plus 1. Okay, so for V2, so this one is 2 Vm, okay, over pi 1 minus 1 plus 3. Okay, so this one should be 1 over 1 plus, okay, multiply with 2, multiply with Vm is 100 over pi. So you should get 84. This one 84.9 volts over your Z2. Okay, so this one is Z2. What is your Z2? So actually Z2 is actually R2 square. R, not R2. This is the R is actually a constant value plus N omega L square. Okay, so your R is maintained one as a 100 square plus N is 2, multiply with 2, multiply with pi, multiply with the frequency supply, which is 50, multiply with your own value of the inductor, which is 10 millihenry, and then square. Okay, so this one is actually just an impedance value. So I think you can just use this one. Z2 is equal to R plus J 2 omega L. So what is the value? So this one is 200 plus J 2 multiply. So this one is 6.28. Okay, and then convert into a polar form. So you should get 100 okay, plus 6.28 I. Sorry, 100 plus 6.28 I. So convert to the polar form, you should get 100 with an angle of 100 with an angle of 3.95. But Z2 requires only magnitude, so this one 84.9 over 100 ohm. So this should be 0.84. So this is for I2. Okay, and similar with V2. So it's quite what we call very tedious work. So but we need also V4. Okay, so V4 is 2 Vm over pi using the formula 1 minus the equation n minus 1, which is 3 minus 1 n plus 1, right? Yeah, n plus 1. So 4 plus 1 is 5. So this one, by using the calculator, so this value is 8.5 volts. Okay, and you need also to calculate Z4. So Z4 is R plus J for omega L. So 100 plus J. 4 is 4 multiplied with 2 multiplied with pi. Sorry, multiplied with pi. Multiply with 50 hertz, multiply with 10 millihenry. So you get this one is 12.6 ohm. Okay, and then you need to convert into a polar form. Okay, sorry, 100 plus 12.6 I convert into polar, so still got 100.8. Should get this one 100.8 ohm. Okay, so your I4 is 8.5 volts, 100.8 ohm, so 0.085, I think. Okay, ampere. So this is I4. Okay, so so we have already answered the second question. So the third question, determine the power absorbed by the load. So determine power absorbed by the load is that you need to have P out is equal to I out RMS multiply with R. Okay, so right now I out RMS, okay, is equivalent to this one. Okay, I out square plus summation of IN. Okay, so right now we only consider two IN, which is I2 and I4. So we can use this one. So IO square plus I2 plus square plus I4 square. Okay, so but this one is I out RMS square, so we use this one. So transfer the square, so we become only IO square plus I2 square plus I4 square. So based on the formula that we have already, the value that we have already obtained from the previous analysis, we obtained that IO is 0.636. 0.636 square plus, and then another one is I2. I2 is 0.84. 0.84 square plus 0.085 square. So this one should be, okay, so you have I out RMS square is 1.117 ampere. So from that, okay, your R load is 100, right? So finally, your P out is 1.117 multiplied with R out, which is 100 ohm. So you should get 111.7 watt. So that is the answer. So we have completed the example 3.